Good morning. Welcome to Krishna's classroom. We continue from where we left in the last lecture. We were looking at the consequence of the introduction of the concept of Riemann integral, which is a rigorous formulation of integration. And one of the results that we had earlier was prior to introduction of this, the notion of the integral was, integral is the reverse process of differentiation. That is, after the advent of or after developing calculus and concept of differentiation, integral was looked upon as the reverse process of differentiation, and it was even called the antiderivative. We had sort of elementary functions, and there were methods developed for finding out the integral of a function, which in turn means the following. Suppose f is a given function defined, I am talking about real value functions on R, and capital F is a function with the property that f derivative for x belonging to some interval t, then it is defined for the integral on AB, and also called the antiderivative of So with the given function, if you are able to hit upon a function capital F with the property that f derivative is equal to f, then you call the capital F as an antiderivative of f, which is not at all a satisfactory way in which the integral could be understood. And then a consequence of this was that one could prove f y minus f x equal to integral x to y In short, this is the second fundamental theorem of calculus. So if you have a function defined, so given f assuming say smoothness Smoothness in the sense that it is a continuous. I mean, at least it is a continuous function on the compact interval, and capital F is defined as dt, provided of course this integral made sense. Then f derivative. This is the fundamental theorem of calculus. This is a cornerstone theorem of calculus. Now the definition of integration, or what you call the concept of Riemann integral, the first definition of integration. Rigorously called for a hard look at the fundamental theorem of calculus. The consequence was that one should have a drastic change in the perception of the fundamental theorem of calculus. So then it was no longer possible to say that and all this made sense. If and only if f derivative of so this is the consequence of the advancement that you had on the concept of integration. In fact, one could construct now the various situations that were. So let me list out some of the things that one could do. We list out them. One, it was possible to to construct a continuous function, construct a bounded on AB with the property that such that it has discontinuities at countably many points, still Riemann integral. Integrable, and Gx could be defined as integral a to x rt dt could be defined. However, one could no longer say that G is differentiable Now, this RT that we have constructed is the Riemann function. So that is one consequence, and simultaneously lot of new ideas started coming. This was around the towards the 19th century. So towards the second half of the 19th century, several discoveries were fascinating constructions. Weierstrass constructed a function on the interval 0, 1, which is differentiable, which is continuous on 0, 1 at every point of but lower differentiable. And therefore, for such a function fx, it was no more possible to write this relation fx equal to integral the reason was f derivative was not defined at any point. Therefore, that is the fundamental theorem of calculus. That is fundamental of calculus. Now that's about this kind of function, construction about the function capital F, so that here it is nowhere differentiable on the interval. Therefore, this integral had no meaning at all with f derivative written over there. So you see that the connection that f such a function cannot be written as the integral of some small function ft dt with ft identified as a derivative. This is because the derivative of f did not exist at all. Okay. Now, a further example showed the following. That is 2. So once again, you look at this kind of relationship. One could show that there exists a continuous differentiable function on the interval zero one, such that its such that f derivative of x is a unbounded function on 0 1, and hence not Riemann integral. This function can easily be written out x square sine one by x square, for x not equal to 0 and equal to 0 when x equal to 0. And one could take this function differentiate it. You can show that f derivative x exists everywhere, but you can show that f derivative of x is not a bounded function. Because what happens is, because of this rapid oscillation that takes place in the neighborhood of 0, see that the tangent will be, the slope of the tangent will be getting closer and closer to infinity. So you get an unbounded derivative. However, you see that this function is differentiable, and you can even show that the derivative exists and the derivative is also continuous. Okay. And for this function, f derivative is continuous. It is easy to see. F derivative is continuous. Sorry, it's not continuous. F derivative exists. It's differentiable at all points. Okay. Okay. The important part is this, that it is just unbounded derivative. F has unbounded derivative at all points on the interval 0. One can even construct a function f r with f derivative existing at all points on the interval 0, 1. F derivative is bounded on 0, 1. But f derivative is not continuous. At all points in C alpha or 0 less than alpha is the one where C alpha is the cantus associated with alpha. Further, lambda of C alpha 1 minus alpha and just positive. So C alpha is not a null set. We have already defined what null set is earlier, so just recall the definition. And hence, f derivative does not belong to therefore the fundamental theorem of calculus in the form is no more. See, the difference between the previous example and this is that, see here, the derivative exists everywhere. Therefore, if you look at this equation, could possibly be true. However, what happens is that the derivative is unbounded. Since the derivative is unbounded, you see that this integral does not exist. Therefore, this relation cannot. In the third case, what we have is that the derivative fails to hold to exist or to be integrable because the following reason. That means if the derivative exists everywhere, okay, it's even a bounded derivative. However, it has far too many discontinuities. In fact, at every point in C alpha, it is discontinuous. Now, this is the problem. Therefore, it doesn't exist. It's no more value. So, you see that with the advent of the concept of Riemann integration, the fundamental theorem of calculus as thought to be by eminent mathematicians like Cauchy, okay, failed to lose its charm. Okay. So the consequence was, and this construction is immaculate, something wonderful, where you see that you exploit the structure of C alpha. So on all these kind of deleted intervals, you construct a function which is somewhat symmetric about the central point and then oscillates rapidly and then patched up. This we have seen last time. And therefore you see that the function that you build is Now, I mean, outside this set, the function is set as 0. So you see that this function is differentiable everywhere. Okay, and you can also show that the derivative is bounded. However, you see that derivative has discontinuities. Derivative is defined at every point as discontinuities at all points in CR. Now this is the problem. Okay. So you see that the relationship, the simple-minded relationship that was given as the fundamental theorem of calculus, something like fx is equal to integral 0 to xf derivative e dt, did not lost its meaning as it is. Okay, it is valid only under certain circumstances. In fact, if f is a continuous function on an interval AB, and therefore it is bounded, and therefore it is Riemann integrable. Okay. Because CAB is contained in RAB. Then what you had is this f of x defined by integral 0 or a to x ft dt is a differentiable function function continuous derivative and is such that that is a fundamental theorem of calculus in the form in which it was known earlier was valid under the condition that small f is a continuous. Okay. But otherwise, even otherwise, this integral makes sense. Because a Riemann integrable function may not be continuous. A Riemann integrable function, okay. So even if a function is bounded, it need not be Riemann integrable. So even if a function has a derivative at every point, the derivative need not be Riemann integrable, as we have seen with that oscillator. So all these examples throw a lot of insight into the relationship between f and f derivative. And in fact, Denis' concept of different derivatives, this is what we want to see. Denis, towards the end of 19th century, introduced for a concept of four derivatives. Namely, d plus d minus for a given function. And of course, the function was differentiable derivative at a point if d minus d plus d minus exists and all these derivatives are equal. So these are called the Dini derivatives. So please refer to the book. Either on measure and integration for more details. At this moment, I don't want to go into the discussion of that, but we will do it certainly while we consider Lebesgue integration later. Okay. But what is significant is that this happens. Now, what is the consequence of this? What happens for a Riemann integral function? So, if f is a Riemann integral function and capital F is defined as fx equal to integral a to x f derivative ft dt, then what you can say about capital F? F has bounded Dini derivatives at all points each dE derivative is a Riemann integrable function. And f can be as integral a to x df dt, where df is either d plus f e plus f e plus f d minus f or d minus at each point. Therefore, you see that you don't have a, this is an elaboration on the statement that I made earlier, that if f derivative is continuous, then of course you see that there is a unique representation that you can give, but otherwise you have several representations possible for this function. Okay, so any function that is obtained in the form of the Riemann integral of a is written as the integral of a Riemann integral function. If this function f small f is not continuous, then you see all these problems. Okay, so you see that the complete breakdown of, so the fundamental theorem of calculus as connecting a function with its derivative or I would say that failed to connect a function with its derivative in general. So this is a much better representation theorem. Okay. So you see that these examples that we have discussed earlier is something very fascinating and should be looked into, especially the construction of the function whose derivative exists everywhere on the interval 0, 1, but fails to is bounded derivative, okay, but fails to be continuous on the Cantor set, so that the derivative exists, but the derivative is not Riemann integral. Okay, so now let us go to the another aspect of or another consequence of integration, the integration theory. How some of the beliefs, earlier beliefs, got completely changed or had to be completely revised. Now we try to look at this problem. Interchange of integration and summation. Or equivalent. Interchange of integration and limit. See, initial understanding of a series of made up of functions given by, okay, let equal to 1 to infinity. Consider this series. Assume all fn's are Riemann integral. And f is Riemann integral. Then is it true that integral a to b ft dt sigma here you see that this is actually integral a to b sigma fn, and what you have done is that we have assumed that fn, the summation and the integration can be interchanged and get this form. So our question is this: is it true that this is true? This relation, that means, can you freely interchange summation and integration? Now we'll examine a equivalent version of this. What is the equivalent version? Suppose it's a finite sum. Therefore, it is well defined. So each fn is well defined. Being a finite sum, each Fn is each capital Fn is well-defined. For each n, Fn is well-defined. And you can easily also if all these small fn's are Riemann integrable, then this is also Riemann. Okay. Now you see that integral ft dt or fx is equal to limit n tending to infinity of fnx. That is the equivalent statement of this. Okay. Then the question that you are asking is this. What you are asking is this. Okay. So what is the question? The question that we raise is this. Is integral a to b is the question, or equivalently is a to b f and t dt. So these two are the equivalent questions that you ask. Okay, let us examine this problem. So let us rewrite the whole problem. Let be a sequence of Riemann integral functions Riemann integrable functions on AB let limit n tending to infinity that means we are assuming that the convergence of the sequence for every x belonging to A. There are two questions now. One, of course, is F Riemann integral. And can we write this as integral a to b ft dt equal to because ft is limit n tends to infinity f and t. So this is the question that we ask. So which is equivalent to the question that we have for the series. And in fact, in the earlier works of Fourier, he assumed that it is possible to execute the integration term by term, even in infinite series, and get the results. Okay, so that was the early notion. But however, it had to be, when it was looked at, this question was looked at more rigorously, then it was found that something which cannot be taken for granted. And that's the interesting part. So let us take the problem. Now, to understand this problem and the intricacies involved, we will examine a few interesting examples. So let us look at the examples and then possibly write down some results which are probably, which can be proved. Okay. So the first example that we look at is the following. Yeah. Define on the interval 0. You know that each one of these functions is a nice continuous function, and so Fn belongs to a nice continuous function which is bounded. Each one of this is bounded, and therefore it is Riemann integral. Okay. Now we ask this question: what happens to Fn? You see that Fnx goes to 0 as n tends to infinity on that means except at the point 0 it goes to 0 as therefore the limiting function is identically on what is we leave out this point, and could be said to be unbounded at, or at the point 0. Therefore, you see that f is not therefore obviously one cannot talk about the integral of f. Okay, so the question does not arise. Or you can say that integral 0 to 1. Because this is not Riemann. This is what happens. Yeah, it's only at a single point where the problem comes. Okay, so the integral would turn out to be 0 once you introduce the concept of Lebesgue integration. You can easily see that this is Lebesgue integral and the integral is 0. And in that case, of course, this limit goes to self. But now what could be the reason for this? Now we make the following observation. No uniform convergence. That is, F1 does not converge. Converges to converge. Uniform. So this is something that we make an observation, and later we shall see how this uniform convergence plays some role in allowing this interchange, permitting the interchange or making the interchange feasible. Okay. Let's look at another example. As you know, the mathematics is born out of an extensive investigation on examples. Okay. Look at this example. It's of a different type. Second example. Let R1, R2, R3, etc. be an enumeration of the set of rations you know that it's a countable set, therefore you can enumerate. Okay. Now let's define one. It takes only two values for x belonging to R1, R for each n, and 0 x belonging to slash what about the limiting function? The limiting function is going to be, or you can observe that Fn belongs to R0 because it has discontinuity only at finitely many points. It's a bounded function and has discontinuity only at R1, R2, etc. finitely. So has bounded and discontinuous. Or it has discontinuities only on a null set. Therefore, see that Fn belongs to R0. And Fx is equal to limit n tending to infinity of is essentially the characteristic function of Q. What is this? That is the function which takes the value 1 at all rational points and 0 elsewhere. What about this function? Is this? So obviously f does not belong. This is what is called the Dirichlet function. The Dirichlet function is not Riemann integral. It's nice to see. Go through the definition and prove that this is not Riemann integral. And therefore, one cannot, make this statement that integral 0 to 1 Fn d dt c is equal to integral 0 to 1 f d dt. Once again, the convergence is not uniform. And so one of the consequential theorems that you can prove is this. I am not going to do that. If Fn converges to F uniformly and all the Fn are Riemann integrable functions, okay, then you can assert that f is a Riemann integral function and the interchange of limiting process and integration. So, what one can show or prove is sequence of Riemann integral functions on an interval AB and Fn converges to F uniformly on AB then F belongs to RA and integral A to B Ft dt equal to limit n tending to infinity integral A to B Fnt. That means, see, if you write this is Ft is limit n tending to infinity Fnt dt, and you have interchanged the integration and the limiting process when you wrote this. I have skipped the intermediate step. Okay, so this is okay. So you see that in both these examples that we have looked at, the problem is that Fn does not converge uniformly to F. Okay, but this is only a sufficient condition. Okay, as we shall see in the next example. Next example is it's not a sufficient, necessary and sufficient condition that we have. We have only established a sufficient condition. Let's look at the example 3 where take Fn x to the power n for x belonging to 0, 1. Now you can show that Fn x converges to f of x, which is equal to 1 at x equal to 1 and 0 x belonging to 1. This one is excluded. Now here you see that the convergence is not uniform. Because you see the sort of function is nice to know the graph of these functions. The function is this one, this is this, and so on, and eventually just, so this is F1, this is F2, F3, and so on, and Fn is something. This is Fn. Now you see that as n tends to infinity, this would finally break up and give you the value 1 here and 0 elsewhere. But the convergence is not uniform. But f belongs to, because it's a bounded function which has only a point of discontinuity, namely 1, and whose which is a null set on which the function is discontinuous, and therefore it is Riemann integrable. and integral 0 to 1 ft dt equal to 0. Because the function is everywhere except at one point 0, and integral 0 to 1 fn t dt, this is equal to 1 by n plus 1, which converges to 0. So you see that this function or this particular example cannot come under the purview of the previous theorem, because you see that the convergence that you have is not a uniform convergence. But nevertheless, you see the result holds. That is, the resulting function f, or the limiting function, is a Riemann integrable function, and integral 0 to 1 fn t dt equal to integral ft dt. Therefore, what I can say is this, that this example does not fit into the framework of the previous theorem. Nevertheless, f belongs to and limit n tending to infinity so that of course gives out some further room. So even if no uniform convergence is there, one could interchange the limit of integration, and if under some circumstances, so see, you are going to have some additional condition. In fact, in this context, you have the theorem by Arzelus. So, let sequence of functions in array. They are all Riemann functions on the interval AB. Assume that for some m positive, mod fnx is less than m for every x belonging to it is all, they are all bounded functions, okay, with a common bound m. Now let f be Riemann. where f is equal to limit So we assume that the functions fn point-wise converge to a Riemann integrable function. Then you have integral a to b dt equal to integral a to limit n tending to infinity of this integral a to b. That means the interchange of the integration and the limit is valid in this case. Now, this is one assumption. In fact, this in the uniform case of uniform convergence, one could get f to be Riemann integral. Whereas here, we did not get that. Okay, we cannot make a statement. In fact, you can see the first two examples you can examine, and you see that those functions, okay, the first example, the class of functions is not uniformly bounded. This is one problem. In the second example, these functions are uniformly bounded by m equal to 1 in fact. However, you see that the limiting function is not real. So the first example fails because of the unboundedness problem. And the second example fails because although you have a common bound for all the fn's in the second example, you see that the limiting function, the limit exists, the limiting function is not a Riemann function. So it fails to satisfy the conditions, one or other of the conditions of this particular theorem. Okay. Yet another exercise or example that you can look at is a similar kind. You see that another example is what you looking at. Okay. Let us consider the sequence of functions on the interval 0, 1. Or we define fn as follows. One at k by 2 to the power n, x not equal to zero but we let 1 less than or equal to k minus 1. Therefore, each of these functions has a discontinuity at finitely many points. They are bounded. So you see that Fn belongs to 0. And see that 0 less than or equal to Fnx less than or equal to. So bounded for every Fn belonging. Now what you have is this. Fn converges to F, where f of x equal to one when x is not equal to a by 2 to the power n, for any n 1 less than or equal to k, and 0 for so we get the set of points defined, and you see that the collection of the set of points 1 k by 2 to the power n with 1 less than or equal to k less than or equal to 2 to the power n for n equal to 1, 2, etc. is dense zero 1. Okay. Therefore, you see, you look at this function. I mean, first of all, the convergence is not uniform. That's for sure. And the second aspect is that it's a bounded set of functions, but you see that the limiting function is not Riemann integrable. Therefore, you see that the interchange of limiting process and the integration process does not come under this theorem or the other theorem. Okay. So you see that this is dense in 0, 1. Therefore, F does not belong to it neither conforms to the first theorem nor conforms to the second theorem. Okay. Therefore, you see that the interchange of limiting process and this is not valid. Okay, that gives some insight into the problems that we encounter having introduced Riemann integration. But the major drawback of the shortcoming is that the space of Riemann integrable functions or RAB with a integral metric is not complete. So the completeness the lack of completeness of this RAB with integral with the DFG defined as integral A to B mod F minus G is a major problem to do analysis on this space. Okay? Therefore, there are a few questions that come up, namely, what exactly is the completion of this particular metric space? Because you know that every metric space has a completion. Can you give a concrete manifestation of this particular completion of RAB with the metric that I have mentioned just now? And obviously the Riemann integration is not adequate enough to deal with the situation. So we are compelled rather to think about rehabilitating integration so that many of the problems that we still got created as well as encountered would get resolved in that process. Okay, that of course leads to the so-called Lebesgue integration theory. So henceforth we will be working on the Lebesgue integration theory. Thank you very much. Okay.